Another approach to stability is to look at it from a probabilistic point of view. In slope W, we have implemented the Monte Carlo method, and we can consider the variability of input parameters, and in the end we can look at the probability of failure. There are a variety of input parameters that can be input and provide description about the dispersion in the parameters. As a summary, we have variation in the shear strength parameters, for example, cohesion and phi. We can have a variation in the unit weight of the soil. We can have variation in the pore pressures, variation in line loads, variation in horizontal and seismic coefficients even. There are various options as far as the probability density functions. There's a normal function, a log normal, uniform, triangular, and even a user-defined function using data points, which can be multimodal if necessary. The point is there are a variety of probability density functions available in slope W. When we have a probabilistic analysis, then here are the primary way of describing the dispersion in the values. And so for a mean value, we can describe the dispersion as numbers of deviations, number of standard deviations, and we can also limit the range of the values from a minimum to a maximum value. There are two types of analysis here. One is probabilistic and the other one is distribution via sensitivity. We'll get to the sensitivity one a little later. So here is a distribution function, a normal distribution function, and in the end what we get is a probability density function of the factor of safety, and finally we get a graph like this that gives us the probability of failure when the factor of safety 1. What is the probability of failure? A key variable that comes into a Monte Carlo analysis is what is known as spatial variability. If we had a slope here and a slip surface, and the strength here varies statistically, the question becomes, how often should we sample the strength along this slip surface? Should we sample the strength once for the entire slip surface? Should we sample the strength for each slice for every run? Or should we sample the strength at some specified distance? We will talk about this in the context of a case history in a little bit here, but jumping forward, in order to answer this question, ideally what is needed is a variogram that depicts spatial correlation. We'll come back to this in a bit. So let's look at an example file and look at how some of the dispersion data is entered, and then look at the results and see how we can interpret the results for a typical example. And then we will briefly look at a case history. It's called the James Bay case history. If we go to GeoStudio then and open up the file Probabilistic and Sensitivity. To start with, under the Key in Analyses dialog box, I want to look at analysis 3 and 4. When we look at analysis number 3, we have a tab here, Factor of Safety Distribution. When we click on this tab, traditionally we would do a constant analysis, but now we want to do a probabilistic analysis. When we come to analysis number 4, we will check on the sensitivity option here. But for now we want to do a probabilistic analysis. In this particular simple example here, we will do 2000 Monte Carlo analysis on the trial slip surface, and it is here where we can select spatial variation, sampling each slice, or specifying some sampling distance. In this illustrative examples, we will not do any spatial variation, so we will just do a probabilistic analysis. Now you can already tell that we have specified some dispersion on the phreatic surface or groundwater table, and the way you do that is you say key in, pore water pressure, piezometric line 1, and under properties you can adjust the height by for probabilistic and sensitivity analyses. We can adjust the height by some values. The mean height is 0, 1 standard deviation, and we will adjust the minimum to a minimum of -3 from the static case to +3 from the static case. We are going to use a normal probability density function here, which results in this sampling function. You can think of rolling a dice, and the dice will come up somewhere between 0 and 1, and if the dice should come up with 0.4, the water table would be set at approximately -0.2 meters. If the dice should come up at 0.8, the water table or piezometric line would be shifted up approximately 0.9 meters, and so forth. It is on this drop-down list that you can choose which type of distribution, probability density distribution, you want to select: log normal, uniform, triangular, general spline, and so forth. Then we have some dispersion on the shear strength, key in materials. For the embankment material, notice that unit weight, cohesion, phi are all gray, but if we click on this ... you can see that we have specified some dispersion for a probabilistic analysis, once again using a normal probability density function. The mean is 30 and the standard deviation is 3, but we've also overridden that with a minimum of 15 and a maximum of 45 for the cohesion. These values are not used until we get down to the sensitivity analysis. We can do the same by looking at the friction angle phi, Once again, the mean is 40, which was used for the static factor of safety calculation. The minimum is 20, the maximum is 60, and we once again use a normal probability density function. The foundation soil uses strength as a function of overburden, and the ratio of shear strength or undrained strength to overburden can be described by some dispersion, where the slope is 0.45 and the minimum is 0.2 and the maximum is 0.7. We can now click on the Solve button and analyze number 3. And what slope W does, it first of all finds the minimum factor of safety slip surface, and then it does a Monte Carlo analysis on that particular slip surface. So I will turn off this option here and keep the Solve window open after it's finished. And you will notice that we did a static analysis first, and then we did 2,000 Monte Carlo runs. Going then to the results view, we can say draw probability, and we get a probability density function of the frequency of the factors of safety and the variation in the factors of safety during the probabilistic analysis. Once this is known, it is possible then to view a distribution function, and here is our distribution function, the probability of failure. And in this particular case here, we notice that here is a factor of safety of 1, and we determine the probability of failure. You can look at this graphically, or you click on the data button here, and you see that the actual probability of failure is 7.75%. It is possible to do the Monte Carlo analysis on more than one trowel slip surface. I believe that in this case, if we say draw slip surfaces, you see this 3 stars. It means that we have only done the detail forces and the Monte Carlo simulation on this one trowel slip surface. In the define portion of slope W, we can specify how many Monte Carlo simulation, how many trowel slip surfaces on which we want to do the Monte Carlo simulation. Very quickly, we can go back to the define view and look at analysis number 4, sensitivity analysis. I won't spend a lot of time here except to just very briefly look at the results. If we analyze number 4, click on the Start button, and then look at the results view, and we say draw sensitivity. You see a graph like this. the blue line, the red line shows how the factor of safety changes with the variation in unit weight. The red line here shows the variation in factor of safety over the range that you have specified for the change in cohesion. And the green line shows the change in factor of safety for the range of friction angles that you have specified. In this graph, we have normalized the sensitivity range. So for example, for the friction angle, we had a range. The range in the friction angle has been normalized to go from 0 to 1, and the unit weight, whatever the range is in unit weight, it also has been normalized to a sensitivity range of 0 to 1. These curves, they all cross over at the 0.5 value, and this point here represents the static case. This simply gives a picture of how the factor of safety changes within the range that you have specified in your dispersion of the data. Going back to the define view under key in analysis, for the fourth analysis under f of s distribution, notice that we had selected sensitivity. This shows you briefly of the types of things that are possible with a probabilistic analysis in slope W. I want to just spend a few minutes now on a case history. Let us say File, Open, Probability, James Bay Case History. As with all of the details examples we ship with slope W, a PDF file describing the example comes with the example, and I refer you to this PDF that comes with this example for the details. It is a very interesting case history that has been mentioned in the research literature several times, but what I want to draw your attention to here is that under the analysis tree, you can see that we have the deterministic case. We can see what happens when we sample the soil strength every slice, or every 30 meters, every 40 meters, or every 100 meters. All I want to draw your attention to as analysis number 3, for example, under the f of s distribution, notice that we have selected spatial variation, and we have said that we will sample the soil every 30 meters. So for every 30 meters along the slip surface, we, so to speak, recast the dice and redetermine the strength along the slip surface. Now, it is hard to imagine that if you had a very long trial slip surface like this, notice that this is nearly 150 meters long, that if you were to cast the dice once for the entire slip surface, that the strength would be at some probabilistic low value over the entire slip surface. So how often should we sample the strength? Well, another alternative is, as we show here, sampling every slice. Now, if we throw the dice, so to speak, for every slice and determine a new strength for every slice, interestingly enough, the solution tends toward the deterministic case. which also doesn't seem realistic. So once again, I refer you to the paper that goes with this case history. I have copied the PDF file and document that goes with this case history to the CD in the folder called Papers of Interest. You can read the article where I discuss the effects of the sampling distance. The fact is that sampling distance is an important parameter in some cases. The unfortunate part, to do it properly and know exactly what an appropriate sample distance should be, you need what is called a variogram, which correlates strengths with distance. I won't go to any detail here. Once again, I refer you to the PDF document that goes with in this detailed example. I am going to leave it at that. It gives you a very brief introduction to the types of probabilistic analyses that are possible with slope W, and I leave it with you to study it in further detail if this is something that you want to use in your projects. This brings us to the end of this workshop session.